All right. So, yeah, welcome back, everyone, from lunch. As Brian was saying, I'm David Power with Boston, and today I wanted to speak about one of our sort of sideline projects that we're working on with Boston, which is our Viridis server. Um, so, with that said, what I'd like to do is I'll just introduce the product and then run through the actual architecture with you, and then finally, then we'd like to wrap up then with some sort of customer use cases and benchmarks to give you an idea of where we find appropriate use cases for our product. So just to introduce Boston, I mean, we've been operating for 21 years at this stage. We have offices throughout the globe in the UK, Germany, India and the US. We were Calxeda's global launch partner for the Viridis product. This happened at ISC back in 2012. And we were the first company to actually ship production-ready ARM servers as well, way ahead of a lot of the Tier 1 vendors. So yeah, this is a product that we've actually been shipping to end users for over 12 months now at this stage. And yeah, we're very proud of the fact that we were one of the first to market with this. Just a couple of highlights from awards and reports that we've had in the media over the last year or so. So we were the Green IT Awards winner a number of months back during the summer, which we were very proud of. You can see a couple of other quotes there that sort of promote the fact that this is a serious threat. ARM in general as a sort of serious threat to the whole current ecosystem. So we got to see our own cool server of 2012, which was nice as well. Okay, so why did we even start looking at this? So I mean, we were kind of taking a look at our standard product range, and the market was kind of going in a direction where we were getting kind of incremental improvements with additional cores, additional performance. But these were only sort of minor improvements every sort of release. We wanted to kind of take a step back and completely re-architect a system that was designed around pure efficiency from the ground up, which would result in an order of magnitude improvement in performance and efficiency. So we achieved this by working with our partners ARM and Calxeda to bring ARM-based products to market, which integrate fabric management and other I/O innovations as well around the standard cores. And the combination of all of this can result in 1/10 of the energy in space and then half the TCO in comparison to standard servers that we see today. So, as many of you will be familiar with in the data center, it's a very much dynamic landscape that's changing at the moment. We feel that we're entering into a new era of computing. So if you take a look back over the years, we've had clearly the clock wars back in the early 90s. This was when people were just trying to ramp up the gigahertz of the actual clocks or cores themselves. We then entered into an era of multi-core, where more and more cores were used to achieve this increase in performance and align with sort of Moore's law increase. And we believe over the next decade or so, we're really going to see a real focus on the efficiency of servers as well. So this will be the performance per watt. We feel that this is going to be the next massive change, or the next sort of focus from a lot of vendors. So target applications and benefits. Again, our product is fairly flexible, and it does address quite a lot of the workloads today. I think as we have quite a HPC focused audience here, it's worth noting that this is perhaps not the ideal product today for floating point intensive codes, but given that this is a very first attempt at an ARM based product in the market space, we've actually had very successful reports from customers in the life sciences and biomedical HPC application space, where we look at more integer based codes. And I'll run through some of that benchmarking later on in this talk. But yeah, analytics and big data, again, great target applications for this platform. Okay, so to enable this energy efficient system, and of course it's considered a software-defined data center as well, we have the integrated system on chip, or SOC. And this is a complete server, so you've got your CPU, your memory, your networking, all of this on the actual single chip itself. And again, the main pain point that this addresses is, of course, you're really improving the performance per watt. We've got this scalable fabric that's integrated as well, so we can have hundreds and thousands of nodes connected via 10 gig fabric. Again, all of this is fully integrated into the server itself. And again, this lowers your infrastructure costs and optimizes for the performance per watt. Each 10 gig port we have on here operates down in the milliwatts of power. And then smart as well. So when we're running, clearly there's a lot more complexity involved in running lots more servers. So for one Intel server, we might have to run 10 based ARM servers, and that increase in systems corresponds, of course, to complexity. So we've got very intelligent management engines in there that do cluster level system optimizations and power optimizations as well. Okay, so the starting point for our system is this individual ARM SOC. This complete system that you see here, which includes your cores, switch, management engine, and I/O and RAM, all typically runs at 5 watts per node. There are some figures coming up later on in the talk that will actually look at the power under load using applications like Stream and Linpack. But yeah, this is our starting point for a server. And just to put that in context, if you were to compare that to a standard dual socket x86 system, that corresponds to somewhere between 200 and 300 watts. So we're talking about potentially a 60x decrease in power. If we step through the actual architecture, what we have here is a standard Cortex A9 based CPU. So this is a quad core, and it runs at about 1.4 gigahertz. We then have each SOC has an internal 8-port 10 gig switch, and again this can be used to scale out the actual fabric throughout many servers. We've an integrated management engine, so this isn't it's not just IPMI for power management or anything else like this. There's a number of intelligent services that can actually run on here to detect what's happening on the system and ensure that all of the components are clocked down or clocked to the actual appropriate levels for power and performance. And again, we have our I/O controllers in here for disconnectivity and SATA and so forth. So the stepping through those kind of features, if we look at the server management, and again, this provides you with the same sort of stuff that you'd see with typical IPMI implementations. But we also have extensibility within here. So the actual hardware itself has hundreds of hooks that we can actually tie into from a very low level. Even though I sort of mentioned earlier that this was a 4-core system, there is actually one ARM core held back in reserve to actually run this management engine. So all of the management that's going on and monitoring is done outside of the actual SOC. It can actually plug into the counters below at a hardware level without actually introducing any sort of OS jitter or interruption on there. So we can actually develop APIs that will allow user space programs plug into this low-level hardware and identify when burst detection is happening within the fabric, or when temperatures are getting above a certain amount, or we have very low-level granularity of control across the system. And of course, this does fabric management as well. So as soon as the system is powered up, we of course have a discovery period where we actually develop all the routing across the system, and in the event of any nodes dropping offline or anything else, the management engine will detect this and implement appropriate rerouting. So the advantages are fairly obvious from that. So again, all this management and intelligence allows you to really optimize the system, reduce the power and reduce the cost. So that's all good for the end user. The fabric itself as well. So again, having this integrated network controller across the system, minimizes the amount of actual switches that you need. We're able to cable our servers together using an actual fabric link in our new model of server. So we've got a very well balanced architecture with huge amounts of bandwidth across a low latency fabric to address all of this, and various other different pieces of functionality there with tunnels and fault resilience and so forth. So once we start to build up this individual SOC, what's the sort of the minimum building block that we actually provide? So this is just the simple example of the most basic cluster that we can actually put together. It's just a 4-node Viridis cluster. It's one of our energy cards. And you can see here the nodes are completely interconnected. We can put up to 4 drives per host. This entire cluster will only consume 20 watts. And again, this is what it actually physically looks like. So this is that 4-node cluster. It looks just like a fairly long PCI type device. And again, within here you have 80 gigs worth of bandwidth, 4 operating systems, 4 SSH ports. And again, you can communicate using TCP/IP, low latency and high bandwidth between all of the nodes. So you run your MPI applications across here as you would on any other standard server. And again, you take this building block and you can scale this up to hundreds or thousands of server nodes. And it also implements a distributed layer 2 switch as well. So that's that. So again, using this fabric, then we can actually optimize for sort of larger scale deployments. There are two fabrics on the latest revision of the system we have. One of the fabrics is for an external or uplink back to a core network, and then we have an internal fabric link which will allow us to link systems together in either just a mesh or torus topology. This is just a sample cabling view of what we do across kind of 3 racks with our system to achieve a 2D torus. And this is the actual product itself. So this is the 2U variant. So you can see there the energy cards that we were actually looking at earlier. This is our 4 ARM-based servers, and then there's 12 of them inside in an actual 2U chassis. So this is 48 servers inside in a 2U. Again, very, very power efficient. This is one of the world's first production-ready ARM servers, all of the integrated fabric, and 4 gig per system. We have a blog site as well that we've been updating with various different reports and benchmarking and user information. So if you go to lowpowerservers.com, you'll see various different reports and news items about the product. We have a 4U variant as well, which is targeted more towards the scale-out storage partners we have. So this was actually one of the platforms validated with Ceph and Inktank. Again, same sort of baseboard, 48 potential ARM-based servers in there, but we can put either 36 3.5-inch disks or 72 2.5-inch drives in there. So if we look at the roadmap as well, we're down here at the moment currently on Cortex A9. The platform we have, there's a lot of talk about how ARM isn't really perhaps going to be applicable until 64-bit. And that's not necessarily true for a lot of applications. For light workloads, analytics, and scale-out storage, the platform we have today is performing very, very well and showing very interesting performance per watt metrics. But the Viridis server itself, we've got a triple play on pin compatibility with our SOCs. So even if people are interested today in testing out ARM, starting to migrate codes over onto ARM, this platform is drop-in replaceable for A15, which will introduce virtualization capability, and A57, which is the first of the 64-bit products. So you have a nice sort of upgrade path there on our system as well to get you to 64-bit, hopefully by sort of mid to end of next year. And then the 3rd generation fabric will soon we start to see some very interesting stuff on the 64-bit platform. So software, again, we've actually had a couple of these servers available for people to remotely access and benchmark on, and one of the most common feedbacks we get is that people don't even realize they're on ARM sometimes. So if they're just using their standard applications, Make, GCC, OpenMPI, unless you're digging around in proc CPU info or dmessage, people don't even realize that they're actually running on ARM. So it's a very familiar environment, has lots of the applications that people will be used to and familiar with. This is some of the more sort of HPC oriented, so you have ARM optimized BLAS libraries, OpenMPI for your applications, FFTW, ScalaPack, all these guys that we're all very familiar with in the HPC industry. So they're all just ready and installable straight off the repositories for Ubuntu, Fedora. SUSE's been added to this as well, and we've done a bit of work with the Debian community and getting Wheezy up and running on here as well. So yeah, very, very familiar environment when you're running on ARM. Some additional stuff that we've actually been working on as well. So only last week we did an announcement with the guys from Eltex. These guys have a binary level translator which can run x86 based binaries on top of ARM. So there has been a number of instances where customers have been using kind of closed source ISV based applications. The problem, of course, just take those on there. You typically have to go through a rebuild and a make to produce a binary for that platform. With this technology, we can actually do binary level translation of the x86 binaries onto ARM. So this allows us to run closed source modules or proprietary modules on top of our hardware. Yeah, the user space, yeah. So there's if you go to just user space, yeah. So it's kind of like almost SEH root environment that you can go into and then just run your environment. So there's there's a number of benchmarks up on low power servers where we did some I think it was seismic processing benchmarks running this, and there is a penalty in running this. It's not recommended for sort of HPC applications, but it is that way to ease the transition for customers that are running any sort of closed source applications. And then other stuff as well. So we have the Fraunhofer parallel file system on there. as a sort of Lustre alternative as well, and we're actually seeing some really good figures with that as well. And of course, Ceph for the scale-out object storage as well. So these are real figures taken in the lab when we were actually running various different benchmarks. So this was a full server, 24 nodes, 24 SSDs, and this power is actually measured at the wall. So we're taking into consideration power supply efficiency, fans, cooling, all the rest of that. And you can see there, Linux on idle is about just over 5 watts. And when we're running intensive applications like Stream or Linpack, we're only going up as far as kind of 7 or 8 watts. So again, really, really low power system. And you can actually compare almost one of the a full 24 node ARM cluster to a low power dual socket x86 system. Some customer reports. So the guys over at the University of Luxembourg and the Poznan supercomputing area kind of joined forces to do a bit of work to have a system out there. This was a paper that was submitted to the Large-Scale Energy Efficiency Conference a while back. So they took our Viridis platform and compared it against Intel's Atoms and AMD's. And they considered not the actual runtime of an application, but the overall power that was consumed during the runtime of that application. So when you start to look at kind of the most energy efficient platform across a number of very familiar benchmarks, so the OSU MPI tests, HPL, C-Ray, Hammer, all applications that you'll be very familiar with. The Viridis platform was always one of the most energy efficient platforms in that it always took the least amount of power to complete the actual benchmarks. So if you're not worried about how long it takes and you are concerned about the power bills you have, this is shown to be sort of in amongst the platforms we have available today, and x86 is a very competitive platform. They also looked at the Green 500 ranking, and against all of the systems that they pitched against, we were sort of ranked the highest based on their theoretical projections. So a while back as well, the guys at the Fedora project migrated all of their ARM-based builds over onto our platform as well. So if any of you are running Fedora 19 on your Raspberry Pis or anything like that, a lot of the build would have actually been done on our platform. So they've got close to sort of 100 servers, and that's actually brought their ARM-based distribution builds in line with their x86 ones as far as release times are concerned. So if you were looking back at 17 and 18 for Fedora, they typically release the x86 ISO, and about a week or two later the ARM one would follow on because of the limitations they had within their build facility. But now that's all been completely accelerated using our platform, and they now have a synchronized release platform to allow their ARM builds get out in time as well. So yeah, they went from install to deployment in a very short space of time. We've been doing a little bit of work with the guys at Manchester on the Spinnaker project. So the Viridis platform, it's been used outside of the actual Spinnaker system itself, and we're investigating the use of it as a host system for launching jobs and workload. And again, the Spinnaker one is a very interesting project because it's using, again, a lot of ARM cores to simulate the neural connectivity of the brain. So a very, very interesting project, and we're hoping to sort of be just on the periphery of that to try and get the whole system being ARM enabled for job submission on the edge. The guys at Cancer Research UK, and they had a publication or a paper at the ISC 13 conference just gone, where they actually mapped a load of their biomedical workloads onto Viridis platform. So they took one of our servers, put 24 disks in there, and had a distributed file system. Then they ran another 8 nodes as web servers, 8 nodes as database servers, and 8 nodes as compute servers, so LAMP stack and parallel scheduler and everything else. And they turned this one box into a full cluster for running these biomedical workloads. And again, you can see more of the results at the actual abstract down there. But yeah, the performance per watt metrics that they found were very, very encouraging across lots of HPC applications. So it was one Viridis chassis, 48 nodes, 24 of them were set up as a Ceph distributed file system, and then there was 8 nodes each for doing web serving, databases, and then just compute itself. So it was all internally just within the same chassis, same fabric. But yeah, it was essentially like kind of one of their cluster setups that they have internally in their data center. So if anyone's interested in getting a sort of remote access to some of this platform for either porting their code or just benchmarking it, we have an ARM as a service facility as well, where people can just sign up and log into the system. This comes with various different pieces of software from our partners like Eltex and Eltex to allow you to do profiling and debugging of your system, as well as potentially running it in emulated mode. And yeah, just to wrap up then, if you were interested in any more background reading, we have, of course, our blog that I've mentioned, and there's lots of different videos, benchmarks, comparisons, and lots of other stuff on there. So please do visit and take a look if you're interested in learning a little bit more. And with that, thank you very much for your time. If there's any questions, I'll be happy to answer them, or feel free to grab me during a coffee break. Mm-hmm. Well, we're using the sort of the ARM reference core design, so it's really sort of related to ARM's release for their 64-bit stuff. So it's an ARM 64-bit product, but what Calxeda have is they've got the fabric and the management sort of and the innovations around that core to try and differentiate there. It's standard core from ARM, yeah.